Hello everyone. Today we are going to calculate the deflection of laterally loaded pipe. Let's take a problem on say a long pipe is embedded in dry sand. So this is the dry sand. The value of horizontal subgrade modulus eta h is known to us as 10,000 kilonewton per cubic meter. Let's say this pipe is subjected to a force of 50 kilonewton at the ground level. And the length of the pipe is say 20 meter, and the diameter of pipe say 1 meter, and the flexural rigidity of this pipe say 80,000 kilonewton meter square. So we want to find out the maximum, calculate the maximum deflection of three-headed pipe as you know that it is a three-headed pipe, and the maximum deflection under the horizontal force which is given to you as Q at ground level is 50 kilonewton. This is given. Naturally, the maximum deflection of this pipe will be at the ground level. It will deflect like this. So maximum deflection will be here. So you will have to find out the maximum deflection of the pipe. You can use Rees and Matlock method. So for this problem, first of all, let's calculate the relative stiffness factor. So we have to calculate relative stiffness factor, capital T, which is going to be fifth root of EI of pipe material divided by horizontal subgrade modulus of the soil, eta h. So here in this problem, we can calculate the value of T, which will be equal to, as you can see, that the flexural rigidity is 80,000 and eta h is 10,000. So 80,000 divided by 10,000. If you calculate this, it is 1.515 meter. So the value of T has been calculated. Therefore, whether it is a long pile or not, you will have to calculate a ratio known as length of the pile upon relative stiffness of the pile. So L by T, 20 divided by 1.515 is greater than 5. Therefore, it's a long pile. Having got the values that it's a long pile, we can find out the maximum deflection by using expression for the deflection. So the value of xz, deflection at any depth z, is called xz. The horizontal deflection is given as a coefficient ax, deflection coefficient, into qg tq divided by ei plus another deflection coefficient dx into mg g square divided by ei. So the value of ax and bx are known to us from Rees and Matlock chart or table. You can find out these coefficients at any depth. So to find out these coefficient, deflection coefficient, you need to calculate capital Z, which is depth upon T. And since maximum deflection is at ground level, therefore capital Z equal to, at ground level Z will be 0, so it is 0. So for capital Z equal to 0, the value of Ax is 2.43 and value of Bx is 1.62. So we can find out from the table given by Rees and Matlock. Having got these values, Ax and Bx are known to us. Now in this problem, the value of mg, moment at the ground level, is 0 and qg is 50. Therefore, we can calculate the maximum deflection x at z equal to 0. This will be the maximum deflection. So maximum deflection under the horizontal force is going to be equal to 2.43 multiplied by qg. Qg is 50 kilonewton into tq. Tq is 1.515 cube divided by flexural rigidity, which is 80,000 kilonewton meter square. So the value of xz, maximum deflection, you can calculate it, and whatever answer we get it, we can find it. So let us calculate this quantity 2.43 multiplied by 5 into 1.5 raised to power 3 divided by so this gives you the value comes out to be 0.005 to meter. So this is the value that we are going to get it. So in millimeter, if you calculate it, it will be multiplied by say 0.005 into 1000 millimeter. So you can calculate it. It would be 5. So there is the maximum deflection at ground level. Similarly, at any depth, we can calculate the deflection. Say at 0.5 meter, if you want to calculate the deflection. So you want to calculate x horizontal deflection at z equal to 0.5 meters. So from the ground level at 0.5 meter, you can calculate it in a similar way. You will have to find out the value of the coefficient and substitute all the values, and you can calculate at any, and then you can plot the locus of the reflection of this path, how the reflection is going to change over the length of the pipe can be easily calculated. Thank you very much.